maximum revenue is 240 times 400. When you multiply those, you get 96,000. And so the improvement is just the ratio of those two. 96,000 divided by 90,000 is equal to 1.07. And what that means is a 7% increase. And anybody would be thrilled to get a 7% increase in their business simply by changing the price and increasing the overall revenue. So let's summarize what we found here. If you lower the cost by 20%, go from $500 per year to $400 per year, assuming all of our other information is correct, then you can increase sales by 33%. That's more than the 20 that you had. And that increases total revenue by 7%. And so we can optimize the price to get the maximum total revenue. And it has to do with this little bit of calculus and the derivative of a function. So in sum, calculus can be used to find the minima and the maxima of functions, including prices. It allows for optimization, and that in turn allows you to make better business decisions. Our next topic in mathematics and data principles is something called Big O. And if you're wondering what Big O is all about, well, it is about time. Or you can think of it as how long does it take to do a particular operation? It's the speed of the operation. If you want to be really precise, the growth rate of a function, how much more it requires as you add elements, is called its order. That's why it's Big O. That's for order. And Big O gives the rate of how things grow as the number of elements grows. And what's funny is there can be really surprising differences. Let me show you how it works with a few different kinds of growth rates, or Big O. First off, there's the ones that I say are sort of just on the spot. You can get stuff done right away. The simplest one is O1, and that is a constant order. And that's something that takes the same amount of time no matter what. You can send out an email to 10,000 people, just hit one button. It's done. The number of elements, the number of people, the number of operations, it just takes the same amount of time. Up from that is logarithmic, where you take the number of operations, you get the logarithm of that, and you see it's increased, but it's really only a small increase, and it tapers off really quickly. So an example is finding an item in a sorted array. Not a big deal. Next one up from that. Now, this looks like a big change, but in the grand schemes, it's not a big change. This is a linear function where each operation takes the same unit of time. And so if you have 50 operations, it takes 50 units of time. If you're storing 50 things, it takes 50 units of space. So find an item in an unsorted list. It's usually going to be linear time. Then we have the functions where I say, you better just pack a lunch because it's going to take a little while. The best example of this is what's called log linear. That's where you take the number of items and you multiply that number times the log of the items. And an example of this is something called a fast Fourier transform, which is used for dealing, for instance, with sound or anything that's over time. You can see it takes a lot longer. If you got 30 elements, you're way up there at the top of this particular chart at 100 units of time or 100 units of space, or however you want to put it. And it looks like a lot, but really that's nothing compared to the next set where I say, you're just going to be camping out. You might as well go home. That includes something like the quadratic. You square the number of elements and see how that just kind of shoots straight up. That's quadratic growth. And so multiplying two n-digit numbers. So if you're multiplying two numbers that each have 10 digits, it's going to take you that long. It's going to take a long time. Even more extreme is this one. This is the exponential 2 raised to the power of the number of items you have. You'll see, by the way, the red line here doesn't even go to the top. That's because the graphing software that I'm using doesn't draw it when it goes above my upper limit there. So it kind of cuts it off. But this is a really demanding kind of thing. It's, for instance, finding an exact solution to what's called the traveling salesman problem using dynamic programming. That's an example of exponential rate of growth. And then one more I want to mention, which is sort of catastrophic, is factorial. You take the number of elements and you raise that to the exclamation point factorial. And you see that one cuts off really soon because it basically goes straight up. You have any number of elements of any size, it's going to be hugely demanding. And for instance, if you're familiar with the traveling salesman problem, that's trying to find a solution through the brute force search. It just takes an extraordinary amount of time. And so, before something like that's done, you're probably just going to, turn to stone and wish you never even started. The other thing to know about this is not only do some things take longer than others, some of these methods, some functions are more variable than others. So for instance, if you're working with data that you want to sort, there are different kinds of sorts or sorting methods. So for instance, there's something called an insertion sort. And what you find is that on its best day, it's linear. It's O of n. That's not bad. On the other hand, the average is quadratic, and that's a huge difference between the two. Selection sorts, on the other hand, the best is quadratic and the average is quadratic. It's always consistent. So it's kind of funny. It takes a long time, but at least you know how long it's going to take versus the variability of something like an insertion sort. So in sum, let me say a few things about Big O. Number one, you need to know that certain functions or procedures vary in speed. And the same thing applies to making demands on a computer's memory or storage space or whatever. They vary in their demands. Also, some of them are inconsistent. Some of them are really efficient sometimes and really slow or really difficult the others. Probably the most important thing here is to be aware of the demands of what you're doing, that you can't, for instance, just run through every single possible solution or your company will be dead before you get an answer. So be mindful of that so you can use your time well and get the insight you need in the time that you need it. A really important element of the mathematics and data science and one of its foundational principles is probability. Now, one of the things that probability comes in intuitively for a lot of people is something like rolling dice or looking at sports outcomes. And really the fundamental question, what are the odds of something? That gets at the heart of probability. Now, let's take a look at some of the basic principles. We got our friend Albert Einstein here to explain things. The principles of probability work this way. Probabilities range from 0 to 1. That's like 0% to 100% chance. When you put P, that stands for probability, and then in parentheses, here A, that means the probability of whatever in parentheses. So PA means the probability of A, and then P of B is the probability of B. When you take all of the probabilities together, you get what's called the probability space, and that's why we have S. And it all adds up to 1 because you've now covered 100% of the possibilities. Also, you can talk about the complement. The tilde here is used to say probability of not A is equal to 1 minus the probability of A, because those have to add up. So let's take a look at something also about conditional probabilities, which is really important in statistics. A conditional probability is the probability of something if something else is true. You write it this way, the probability of, and that vertical line is called a pipe, and it's read as assuming that or given that. So you can read this as probability of A given B is the probability of A occurring if B is true. And so you can say, for instance, what's the probability if something's orange? What's the probability that's a carrot given in this picture? Now, the place where this comes in really important for a lot of people is the probabilities of type 1 and type 2 errors in hypothesis testing, which we'll mention at some other point. But I do want to say a few things about arithmetic with probabilities because it doesn't always work the way that people think it will. Let's start by talking about adding probabilities. Let's say you have two events A and B. And let's say you want to find the probability of either one of those events. So that's like adding the probabilities of the two events. Well, it's kind of easy. You take the probability of event A and you add the probability of event B. However, you may have to subtract something. You may have to subtract this little piece because maybe there is some overlap between the two of them. On the other hand, if A and B are disjoint, which means they never occur together, then that's equal to 0. And then you can, subtract 0, which is you get back to the original probabilities. But let's take a really easy example of this. I've created my super simple sample space. I have 10 shapes. I got 5 squares on the top, 5 circles on the bottom. I've got a couple of red shapes on the right side. Let's say we want to find the probability of a square or a red shape. So we are adding the probabilities, but we have to adjust for the overlap between the two. Well, here's our squares on top. 5 out of the 10 are squares. And over here on the right, we have 2 red shapes, 2 out of 10. So let's go back to our formula here and let's change a little bit, change the A and the B to S and R for square and red. Now we can start this way. Let's get the probability that something is a square. Well, we go back to our probability space. You see we have 5 squares out of 10 shapes total. So we do 5 over 10, that reduces to 0.5. Okay, next up, the probability of something red in our sample space. Well, we have 10 shapes total. 2 of them on the far right are red. So that's 2 over 10. And you do the division, you get 0.2. Now the trick is the overlap between these two categories. Do we have anything that is both square and red? Because we don't want to count that twice. So we have to subtract it. So let's go back to our sample space. And we're looking for something that is square. There's the squares on top, and there's the things that are red on the side. And you see they overlap. And this is our little overlapping red square. So there's one shape that meets both of those, 1 out of 10. So we come back here, we do 1 out of 10. That reduces to 0.1. And then we just do the addition and subtraction here. 0.5 plus 0.2 minus 0.1 gets us 0.6. And so what that means is there's a 60% chance of an object being square or red. And you can look at it right here. We got 6 shapes outlined now. And so that's the visual interpretation that lines up with the mathematical one we just did. Now let's talk about multiplication for probabilities. Now the idea here is you want to get what are called joint probabilities, or the probability of 2 things occurring together simultaneously. And what you need to do here is you need to multiply the probabilities. And we can say probability of A and B because we're asking about A and B occurring together, a joint occurrence. And it's equal to the probability of A times the probability of B. That's easy. But you do have to expand it just a little bit because you can have the problem of things overlapping a little bit. And so you actually need to expand it to a conditional probability. The probability of B given A. Again, that's the vertical pipe there. On the other hand, if A and B are independent, if they never co-occur, or B is no more likely to occur if A happens, then it just reduces to the probability of B and you get your slightly simpler equation. But let's go and take a look at our sample space right here. So we've got our 10 shapes, 5 of each kind, and then 2 that are red. And we're going to look at originally the probability of something being square or red. Now we're going to look at the probability of it being square and red. Now I know we can eyeball this one really easy, but let's run through the math. The first thing we need to do is get the ones that are square. There's those 5 on the top, and the ones that are red, and there's those 2 on the right. In terms of the ones that are both square and red, yeah, obviously there's just this one red square at the top right. But let's do the numbers here. We change our formula to be SNR for square and red. We get the probability of square. Again, that's those 5 out of 10. So we do 5 out of 10, reduces to 0.5. And then we need the probability of red given that it's a square. So we only need to look at the squares here. There's the squares, 5 of them. And 1 of them is red. So that's 1 over 5. That reduces to 0.2. You multiply those two numbers, 0.5 times 0.2, and what you get is 0.1, or a 10% chance, or 10% of our total sample space is red squares. And you come back and you look at it, you say, yeah, there's 1 out of 10. So that just confirms what we were able to do intuitively. So that's our short presentation on probabilities. And in sum, what do we get out of that? Number 1, probability. It's not always intuitive. And also the idea that conditional values can help in a lot of situations, but they may not work the way you expect them to. And really, the arithmetic of probability can surprise people. So pay attention when you're working with it so you can get a more accurate conclusion in your own calculations. Welcome to Statistics and Data Science. I'm Barton Poulsen, and what we're going to be doing in this course is talking about some of the ways that you can use statistics to see the unseen, to infer what's there even when most of it's hidden. Now, this shouldn't be a surprise if you remember the data science Venn diagram that we talked about a while ago. We have math up here in the top right corner, but if you were to go to the original description of this Venn diagram, its full name was Math and Stats. And let me just mention something in case it's not completely obvious about why statistics matters to data science. And the idea is this. Counting is easy. It's easy to say how many times a word appears in a document. It's easy to say how many people voted for a particular candidate in one part of the country. Counting is easy, but summarizing and generalizing, those things are hard. And part of the problem is there's no such thing as a definitive analysis. All analyses really depend on the purposes that you're dealing with. So as an example, let me give you a couple of pairs of words and try to summarize the difference between them in just 2 or 3 words. I mean, in a word or two, how is a souffle different from a quiche? Or how is an aspen different from a pine tree? Or how is baseball different from cricket? And how are musicals different from opera? It really depends on who you're talking to. It depends on your goals, and it depends on sort of the shared knowledge. And so there's not a single definitive answer. And then there's the matter of generalization. Think about, again, take music. Listen to 3 Concerti by Antonio Vivaldi, and do you think you can safely and accurately describe all of his music? Now, I actually chose Vivaldi on purpose because Igor Stravinsky said you could. He said he didn't write 500 concertos. He wrote the same concerto 500 times. But take something more real world like politics. If you talk to 400 registered voters in the US, can you then accurately predict the behavior of all of the voters? There's about 100 million voters in the US. And that's a matter of generalization. And that's the sort of thing that we try to take care of with inferential statistics. Now, there are different methods that you can use in statistics, and all of them are designed to give you sort of a map, a description of the data you're working with. There are descriptive statistics, there are inferential statistics, there's the inferential procedure, hypothesis testing, and there's also estimation. And I'll talk about each of those in more depth. There are a lot of choices that have to be made, and some of the things I'm going to discuss in detail are, for instance, the choice of estimators, that's different from estimation, different measures of fit, feature selection for knowing which variables are the most important in predicting your outcome, also common problems that arise when trying to model data, and the principles of model validation. But through this all, the most important thing to remember is that analysis is functional. It's designed to serve a particular purpose. And there's a very wonderful quote within the statistics world that says, all models are wrong. All statistical descriptions of reality are wrong because they're not exact depictions, they're summaries. But some are useful. And that's from George Box. And so really the question is, you're not trying to be totally, completely accurate, because in that case, you just wouldn't do an analysis. The real question is, are you better off doing your analysis than not doing it? And truthfully, I bet you are. So in sum, we can say 3 things. Number 1, you want to use statistics to both summarize your data and to generalize from one group to another if you can. On the other hand, there's no one true answer with data. You got to be flexible in terms of what your goals are and the shared knowledge. And no matter what you're doing, the utility of your analysis should guide you in your decisions. The first thing we want to cover in statistics and data science is the principle of exploring data. And this video is just designed to give an exploration overview. So we like to think of this, the intrepid explorers, they're out there exploring and seeing what's in the world. You can see what's in your data. More specifically, you want to see what your data set is like. You want to see if your assumptions are met so you can do a valid analysis with your chosen procedure. And really, something that may seem very weird is you want to listen to your data. If something's not working out, if it's not going the way you want, then you need to pay a little more attention, and exploratory data analysis is going to help you do that. Now, there are 2 general approaches to this. First off, there's a graphical exploration. So you use graphs and pictures and visualizations to explore your data. The reason you want to do this is that graphics are very dense in information. They're also really good. In fact, the best way to get the overall impression of your data. Second to that, there is a numerical exploration. I make it very clear. This is the second step. Do the visualization first, then do the numerical part. Now, you want to do this because it can give greater precision. And this is also an opportunity to try variations on the data. You can actually do some transformations, move things around a little bit, and try different methods and see how that affects the results and see how it looks. So let's go first to the graphical part. There are very quick and simple plots that you can do. Those include things like bar charts and histograms and scatter plots. Very easy to make and very quick way of getting an understanding of the variables in your data set. In terms of numerical analysis, again, after the graphical methods, You can do things like transform the data, that is, take like the logarithm of your numbers. You can do empirical estimates of population parameters, and you can use robust methods. And I'll talk about all of those in more length in later videos. But for right now, I can sum it up this way. The purpose of exploration is to help you get to know your data. And also, you want to explore your data thoroughly before you start modeling it, before you build statistical models. And all the way through, you want to make sure you listen carefully so that you can find hidden or unassumed details and leads in your data. As we move in our discussion of statistics and exploring data, the single most important thing we can do is exploratory graphics. In the words of the late great Yankees catcher Yogi Berra, you can see a lot by just looking. That applies to data as much as it applies to baseball. Now, there's a few reasons you want to start with graphics. Number one is to actually get a feel for the data. I mean, what's it distributed like? What's the shape? Are there strange things going on? Also, it allows you to check the assumptions and see how well your data match the requirements of the analytical procedures you hope to use. You can check for anomalies like outliers and unusual distributions and errors. And also you can get suggestions. If something unusual is happening in the data, that might be a clue that you need to pursue a different angle or do a deeper analysis. Now, we want to do graphics first for a couple of reasons. Number one is they're very information dense, and fundamentally humans are visual. It's our single highest bandwidth way of getting information. It's also the best way to check for shape and gaps and outliers. There are a few ways you can do this if you want to. The first is with programs that rely on code. So you can use the statistical programming language R, the general purpose programming language Python. You can actually do a huge amount in JavaScript, especially in D3.js, or you can use apps that are specifically designed for exploratory analysis. That includes Tableau, both the desktop and the public versions, Qlik, and even Excel is a good way to do this. And then finally, if you really want to know, you can do this by hand. John Tukey, who's the father of exploratory data analysis, wrote his seminal book, a wonderful book, where it's all hand graphs, and actually it's a wonderful way to do it. But let's start the process for doing these graphics. We start with one variable, that is univariate distributions. And so you're going to get something like this. The fundamental chart is the bar chart. This is when you're dealing with categories and you're simply counting how many cases there are in each category. The nice thing about bar charts is they're really easy to read. Put them in descending order and maybe have them vertical, maybe have them horizontal. Horizontal can be nice to make the labels a little easier to read. This is about psychological profiles of the United States. This is real data, and that we have the most states in the friendly and conventional, a smaller number in temperamental and uninhibited, and the least common of the United States is relaxed and creative. Next, you can do a box plot, or sometimes called a box and whiskers plot. This is when you have a quantitative variable, something that's measured, and you can say how far apart scores are. A box plot shows quartile values. It also shows outliers. So for instance, this is Google searches for modern dance, and that's Utah at 5 standard deviations above the national average. That's where I'm from, and I'm glad to see that there. Also, it's a nice way to show many variables side by side if they're on approximately similar scales. Next, if you have quantitative variables, you're going to want to do a histogram. Again, quantitative, so interval or ratio level, or measured variables. And these let you see the shape of a distribution and potentially compare many. So here are 3 histograms for Google searches on data science and entrepreneur and modern dance. And you can see mostly for the part normally distributed with a couple of outliers. Once you've done one variable or the univariate analyses, you're going to want to do 2 variables at a time. That is bivariate distributions or joint distributions. Now, one easy way to do this is with grouped plots. So you can do grouped bar charts and box plots. What I have right here is grouped box plots. I have my 3 regions, psychological regions of the United States, and I'm showing how they rank on openness. That's a psychological characteristic. And what you can see is that the relaxed and creative are highest and the friendly and conventional tend to go to the lowest. And that's kind of how that works. It's also a good way of seeing the association between a categorical variable like region of the United States psychologically and a quantitative outcome, which is what we have here with openness. Next, you can also do a scatter plot. That's where you have two quantitative variables. And what you're looking for here is it a straight line? That is it linear? Do we have outliers? And also the strength of association. How closely do the dots all come to the regression line that we have here in the middle? And this is an interesting one for me because we have openness across the bottom. So more open as you go to the right, and agreeableness. And what we see is there's a strong downhill association. The states in the United States that are the most open apparently are also the least agreeable. So we're going to have to do something about that. And then finally, you want to go to many variables, that is multivariate distributions. Now, one big question here is 3D or not 3D. Let me actually make an argument for not 3D. So what I have here is a 3D scatter plot of three variables about Google searches. Up the left, I have FIFA, which is for professional soccer. Down there on the bottom left, I have searches for NFL, and on the right, I have searches for NBA. Now, I did this in R, and what's neat about this is you can click and drag and move it around. And that's kind of fun. You kind of spin around, and it gets kind of nauseating as you look at it. And this particular version, I'm using Plotly in R. It allows you to actually click on a point and see, let me see if I can get the floor in the right place. You got to click on a point and see where it ranks on each of these characteristics. You can see, however, this thing's hard to control. And once it stops moving, it's not much fun. And truthfully, most 3D plots I've worked with are just kind of nightmares. They seem like they're a good idea, but not really. So here's the deal. 3D graphics, like the one I just showed you, because they're actually being shown in 2D, they have to be in motion for you to tell what's going on at all. And fundamentally, they're hard to read and confusing. Now, it's true they might be useful for finding clusters in 3 dimensions. We didn't see that in the data we had, but generally, I just avoid them like the plague. What you want to do, however, is see the connection between several variables. You might want to use a matrix of plots. This is where you have, for instance, many quantitative variables. You can use markers for group membership if you want. And I find it to be much clearer than 3D. So here I have the relationship between 4 search terms: NBA, NFL, MLB for Major League Baseball, and FIFA. You can see the individual distributions. You can see the scatter plots. You can get the correlation. Truthfully, this for me is a much easier kind of chart to read and get the richness that we need from a multidimensional display. So the questions you're trying to answer overall are, number one, do you have what you need? Do you have the variables you need? Do you have the variability that you need? Are there clumps or gaps in the distributions? Are there exceptional cases, anomalies that are really far out from everybody else, or spikes in the scores? And are there errors in data? Were there mistakes in coding? Did people forget to answer questions? Are there impossible combinations? And these kinds of things are easiest to see with a visualization that'll really just kind of puts it right there in front of you. And so in sum, I can say this about graphical exploration of data. It's a critical first step. This is basically where you always want to start. And you want to use the quick and easy methods. Again, bar charts, scatter plots are really easy to make, and they're very easy to understand. And once you're done with the graphical exploration, then you can go to the second step, which is exploring the data through numbers. The next step in statistics and exploring data is exploratory statistics, or numerical exploration of data. I like to think of this as go in order. First you do visualization, then you do the numerical part. And a couple of things to remember here. Number one is you're still exploring the data. You're not modeling yet, but you are doing a quantitative exploration. This might be an opportunity to get empirical estimates, that is, of population parameters as opposed to theoretically based ones. It's a good time to manipulate the data and explore the effects of manipulating the data, looking at subgroups, transforming variables. Also, it's an opportunity to check the sensitivity of your results. Do you get the same general results if you test under different circumstances? So we're going to talk about things like robust statistics and resampling data and transforming data. So we'll start with robust statistics. This, by the way, is Hercules, a robust mythical character. And the idea with a robust statistics is that they are stable, is that even when the data varies in sort of unpredictable ways, you still get the same general impression. This is a class of statistics. It's an entire category that's less affected by outliers and by skewness and kurtosis and other abnormalities in the data. So let's take a quick look. This is a very skewed distribution I created. The median, which is the dark line there in the box, is right